Yeah, so this school, the main focus of the school, as Subhajit mentioned, is about design, implementation, and verification of computer systems. And one of the important aspects of these areas is that you need some sort of abstraction, right? So abstraction is an important property of specifying systems and verifying systems. So what I will try to do in the next couple of lectures is to uh, basically give you a formalism, right, in order to do abstraction and specification. So design involves specifying the requirements that you would like systems to satisfy, and then of course implementation is you actually build the system. And a very important component of this entire mixture is the verification part, the last part, right? So, uh, well, you can write programs, but it would be useful if you could also show correctness or argue or give some kind of arguments to show that your program is correct, right? It achieves the objectives that you started out with. So that's basically the idea of verification. And in both the design and the verification phases, you need to do some abstraction to specify what the system you want to build is, and finally to verify the system, right? So you want the correctness requirements specified in some sort of a formal language, and the system itself you need to kind of give hopefully finite abstraction. I mean, it's not always possible, but if you can give a finite abstraction of the system, then you can use various tools and techniques to hopefully show that the program or the system that you built is correct, right? So this is very important for large systems, and especially system safety critical systems, right? So what I'll do in the next couple of lectures is look at one such formalism for doing these things, and that is logic. Logic is well, the notion of abstraction is inherent in logic, and it's a very well studied topic, and there are a lot of it has a very deep foundational theory behind it, right? So you can use that as a specification language, as abstraction language. So the point about logic, at least the main message that I would like to convey, is that well, there are two parts to logic. One is the semantics, how you interpret the formulas, and the other is the syntax, right? So it is excellent to do symbolic manipulations in logic. And if you want to automate any kind of verification, right? So, I mean, of course, in large systems, you don't want to prove that the system is correct using pen and paper. You would like to automate the process of verification. And for doing that, it would be ideal to have programs which basically do symbol manipulation, right? Symbolic manipulation. And logic is an excellent framework for that. So these are two messages I will delve upon in this couple of lectures. So as Subhajit mentioned, I mean, most of the rest of the school is more systems oriented. I will not be talking too much about the implementation of many of the things that I'll be explaining, but this will be covered at least in some part in lectures by Subhajit and also Supratik. So I will focus on the theoretical aspects of these concepts. That's basically because of the time constraint, but I will try to, so I'll start with the propositional logic, which many of you would have seen, but I'll try to give you a very formal description of that, so that which is required for various results that we want to show. And it also carries over to more sophisticated logic. So it's like the same recipe that we will follow. Okay. So yeah, so that's basically the idea. And if you have any questions, please feel free to just unmute yourself and ask. I may not be monitoring the chat box so consistently, so just unmute yourself and ask if you have any questions. And again, if some parts are not clear, if you need a better explanation, just ask. Okay, so we'll start with propositional logic, which is something that I'm sure you would have all seen. So what is propositional logic as far as we are concerned? It consists of, so this is the formal framework, right? So I will explain what is the syntax of the logic, and then we'll get into semantics. So the way I will do the syntax is, I mean, there's a particular reason for doing this. So we start with a set of propositions, okay? And you can think of these as the atomic objects of these are the building blocks of the logic, right? So this is allowed to be a countable set. It need not be a finite set. So you have this countable set of propositions. So that's where you start. And then you have some symbols, right? What are the symbols? These are the logical connectives. So you have negation, you have disjunction, and you have conjunction. Okay, so these are the symbols with which you build the formulas of this logic. And how do you define the syntax of the logic? Formally, this is how. So let me just give you this presentation, and probably what you've seen is a different presentation. So I'm going to define the set phi consisting of the formulas of propositional logic. How do I define it? It's the smallest set satisfying the following conditions. Okay, so this is an inductive definition. Okay. So what is the base case? Of course, all propositions are formulas. And if alpha is a formula, then not alpha is a formula. So negation is a valid formula. If alpha and beta are formulas, then you can take the disjunction of alpha and beta. That's a valid formula, well-formed formula, sorry. And if alpha and beta are formulas, then you can also take the conjunction. This is a well-formed formula. Okay, so there is a reason why you define it in terms of this kind of a structural induction, because pretty much any theorem or any result that you would want to prove, it is convenient to have some sort of a structure, right? So you would do it by induction. Induction on what? Induction on the structure of the formula. Okay, so that's why it's convenient to define it this way. Okay, the typical presentation that you would have probably seen, which is also the same, is what is called the BNF, right? So this is how you would write it. This is a very compact way of writing the same thing, what I just said. This defines the set of propositional logic formulas, phi. And what is the syntax? Well, you're saying that every proposition is a formula. If alpha is a formula, is a well-formed formula, then you can take the negation of alpha. That's also fine. If alpha and beta are well-formed formulas, then you can take the disjunction as well as the conjunction. Okay, so this is the syntax of the logic. So the important part here is that this negation is negation here is a unary operator. So negation is a unary operator, and both conjunction and disjunctions, these are binary operators. Okay. Again, so if something is not clear in the slides, please feel free to ask, or if you are having difficulty.
What would be the definition of P, atomic proposition?
Say it again, sorry.
What would be the definition of an atomic proposition?
Yeah, so right now, don't associate any meaning with it. So it doesn't have any meaning right now. Think of it as just symbols, right? So all I'm saying is you have a set, of symbols. Okay, fine. So right now there is no meaning with it, and the only constraint that you're imposing is that this set is a countable set.
Okay.
Okay, so it need not even be finite, right? So it can be infinite, but it's a countable set.
Okay. Okay.
Okay, so it's just symbols, right? Okay. So that's the beauty of logic. So you have a clear distinction between the symbol manipulation and the actual meaning of what you write, right? So we have not reached the meaning of what we write. At the moment, it's just a bunch of symbols, right? So how do you combine the symbols is that's specified by the rules of the logic, and that's what is written here.
Okay. No, but this P has a definition, right? Because the first axiom itself says that every atomic proposition should belong to the set P.
So propositions are the basic building blocks. Now I want to define what is a well-formed formula, right? So I mean, think of it this way. So every programming language, right? Let's for instance C. It has a syntax, right? So so you write a program for you to call or for you to make the assertion that this is a C program. You need to follow some rules which are specified by the C syntax, right?
Yeah.
Now, how do you? So the output of the program is a different matter, right? That you have to execute the program. Yeah. So even before you come to the stage of running the program or execution of the program, you have this this constraint that you have to write your program in a particular way.
Yeah.
Yeah. So, for instance, in C, you can start with saying there are variables, right? Okay.
Okay.
So now there are variables, there are keywords. Now, how do I combine these things, right? So there are these keywords, there are these variables. You can think of these as the atomic building blocks, right?
Okay. Okay. Mhm.
To write the program, how do I actually combine it? There are a set of rules, right? You can't simply write if, then, while. I mean, that's not a valid program, right?
Mhm. Yes.
So what are the rules which ensure that what you write is a valid C program? So that's the syntax.
Okay. Okay.
Okay, so
So
that's what
some
I'm
basic
saying.
symbols and the rules to connect them, basically.
Correct. So this is a set. This phi is a set.
Hmm.
It denotes a set of all well-formed propositional logic formula.
Okay.
So what are the rules for a formula being well-formed?
So
That
just
is
to
what is being
clarify,
described.
so in the first axiom, when we say P belongs to phi, so this P is just a member of that big set P, right? It's just a
Correct. So
member.
correct. So this is a proposition. Yeah.
Okay.
So
Okay.
this is
Okay.
not an axiom. It's a definition, right? I mean, it's not. Don't think of it as an axiom at the moment.
Okay.
Okay.
We are defining.
So
Okay.
yeah, I'm defining the set phi, and every proposition is a well-formed formula, is what I'm saying. So that's where you start.
Okay. Okay. Thanks. Thanks a lot.
Okay. Okay. So I hope it's clear. Any other questions? Okay. So just some simple examples, right?
I
So
just have a small
yeah,
question about the
yeah,
notation. So
yeah.
you've used, I mean, I've seen multiple uses of like equal to's and all that. Can you just, if you could just spell it out loud and like you can, the one
You
that you've
mean
used
this
for,
part, is it?
yeah, yeah.
Okay. So this is just a definition. So this is not a logical symbol. I'm just defining a set. Okay, so
Okay.
you can instead of this, for instance, I mean, you can use your favorite notion of definition. So, for instance of this, you can say use something like this, right? I mean, it's
Correct.
not equality, right? It's a definition. So, for instance, you can use this symbol.
Okay.
I mean, I want to distinguish between equality and a definition. So that's so
Correct.
equality we'll use later. So that's the.
So this one is, you'll be using this throughout for definitions, right?
Yeah, mostly I hope so. Yeah,
Right.
but yeah, so I won't be using equality as much as possible for definitions. Yes.
Okay, cool. Thanks.
Yeah. But again, if something is not clear, just ask when you see inequality. Yeah. Okay, so simple examples. For instance, P and not Q. This is a well-formed formula. Something like this is a well-formed formula. You can have brackets. Yeah. So and brackets is typically required. I'll come to precedence in a minute. But something so and Q is not a well-formed formula because this conjunction is a binary operator, right? So it's not a unary operator, and something like this is also not a well-formed formula. Okay, so P and not Q is not a well-formed formula. Again, these are simple things, right? Okay, so what about operator precedence? The precedence is as follows: you have negation, which is the unary operator, comes first, followed by conjunction and disjunction. So if I write something like this, not alpha or beta, then what I really mean is, or the way you interpret it is, not binds with alpha. So that has the highest precedence, and then followed by disjunction beta. Okay. And it's always a good idea to use parentheses. It's just that sometimes it becomes difficult to read, but yeah, so then there's no confusion or ambiguity. Okay. Okay. So this is what defines syntax. And as I said, for any mathematical treatment or any theoretical treatment of logic, so this doesn't have anything to do with propositional logic. So any logic, right? So what you would ideally want is an inductive definition of the syntax. Okay, because this is the basis that we are going to use, right? So for any kind of result that you want to prove, you need some structure for the formula, and what is the structure that you're using is the inductive structure, right, which is given by this. Okay. Okay, so this is the syntax. It just defines when you say that something is well written or a well formed formula. It doesn't have any meaning. Yeah. So and of course, when you write a formula, you would want to associate some meaning with the formula, and that is what is specified by the semantics, right? So again, these are generic things, right? So this has nothing to do with propositional logic. In any kind of logical formalism that you take, you have these two distinct objects. There is one syntax which defines how to actually write the formula, and there is a semantics which tells you how to interpret the formula. Okay, it's the same way that you have you would deal with C programs, right? So there is a particular way of writing the C program. If you don't write it that way, you get a syntax error, right? And that has got nothing to do with what the program actually does, right? That is that you figure out when you actually execute the program. Okay, so there are a set of rules which you have to follow in order to specify a formula, and how do you interpret the formula, that is given by the semantics. Okay, I hope that is fine. So let's I'll quickly define the semantics. Again, I'm sure that you have seen it in a different form. So I'm going to define it inductively, right? Because that's how it is defined. The syntax is defined. So where do you start? You start with the atomic objects, which are the propositions, right? So what you start with is what is called a valuation. Okay, so it is a function from the set of propositions to true false. Yeah, so these are just two symbols. Yeah, so this symbol I'm going to interpret as true, the top symbol, and the bottom symbol I'm going to interpret as false. You can also put 0, 1, whatever, it doesn't matter. Yeah, it's just a matter of interpretation. Okay, so you start with a function which is from the set of propositions to this two valued set. Yeah, now of course this just defines the meaning of the atomic building blocks, which are the propositions. What we want to give is a meaning for the formulas, right? So what we have is this function from propositions to true false. And what I want to do is extend that function to a function from the set of propositional logic formulas, which is this set phi, to true false. Okay. And how do I do that? This is one way of doing it, and this just to make it consistent with the rest of the lecture. This is how I'm going to define it. So you have a valuation v, which is this function. Okay, so this is the function which specifies the meaning or the interpretation for propositions. Now, this is what I'm going to write. So V satisfies a formula alpha. Now, alpha is a formula, not a proposition, not necessarily a proposition. Okay. So how do I define it? Well, by induction, right? So if alpha, so the base case is when alpha is a proposition, right? So when do we say that V satisfies P? Well, if V of P is true, right? This you have, this is a valuation over propositions. P is a proposition. So if V of P is true, then you say that V satisfies P. So that is the straightforward part, right? Okay, so now if you have a formula, not alpha, again, right? So alpha can be anything, right? It's a well-formed formula, right? Okay, so when do we say that V satisfies a not alpha? If it is a case that V does not satisfy alpha. Okay, so this is why you're doing induction, right? So the notion of the concept of whether V satisfies alpha or not is already defined by induction, because alpha is a formula which is strictly simpler than not alpha. So you say that V satisfies not alpha if and only if V does not satisfy alpha. Okay, and similarly for disjunction and conjunction, you say that V satisfies alpha disjunction beta, alpha or beta, if V satisfies alpha or V satisfies beta. Okay, again, this is this you have by induction. Okay, because these are simpler formulas. So that's it. This is how you define the semantics. Okay, any questions? So I'm not directly building a truth table, which you will see the obvious reason why I'm not doing it. So I'm doing structural induction, right? So the basic object that you have is a valuation, and you define the notion of formula being satisfied under evaluation by induction. So that's how it's defined. Okay. So these are two important concepts or notions in logic. The notion of satisfiability and validity. Again, this has nothing to do with the propositional logic for any logic. For propositional logic, this is how we would define it. We would say that a formula alpha is satisfiable if there is some valuation in the set of all valuations. So this denotes the set of all valuations such that V satisfies alpha. Okay, the way we defined it. Okay, and we say that alpha is valid if for every valuation in the set of all valuations, V satisfies alpha. Okay, so and the typical notation for validity is something like this, right? So you just write this semantic entailment followed by alpha. So there's nothing here. Okay.
Sorry to interrupt. So when we say V satisfies alpha or beta, if and only if V satisfies alpha or V satisfies beta, so
Yeah.
where are we using this OR operator? Are we using it in the true-false set?
So again, maybe I should have emphasized this point. So this object here, right, alpha disjunction beta that I've written here, this is just a symbol, right? Okay,
Yeah.
so this does not have any meaning. Yeah. Now I need to give a meaning. So for the semantics, or in order to interpret this formula, I need to give some meaning for this symbol here. Yeah.
Okay. Okay.
So that interpretation or that meaning is this English word or. Okay.
Okay.
So there's a difference between the symbol and this or here. Yeah. This is just a symbol. Okay. So this is from the syntax, which doesn't have any interpretation. It's just a symbol.
That's an English
So,
or true or true.
yeah. So the way we interpret this symbol is the intended meaning of or.
Okay.
As you would use in English.
Thank
Okay,
you.
so the similar for the conjunction. This is just a symbol, and the way we want to interpret the symbol is this is the meaning of and as we use it in English.
Okay, thanks.
Okay, so again, this is a very important point to always keep in mind when you're looking at logic. All these are symbols. It doesn't have any meaning until you specify meaning, right? I mean, for instance, I don't have to use this symbol, this disjunction symbol. I can use, for instance, if whatever is my favorite symbol, right? Star. I can instead define it as so this object here. I can say something like alpha star beta. Okay, this is how I write disjunction. I mean, it's up to me, right? It's up to you, whatever, right? It's just convention. This is what is typically used. Okay, but as far as the definition goes, it doesn't really matter. Okay, it's just a symbol. Now the interpretation of that symbol is what you define. So these are two different objects. Any other questions?
Just to confirm, a valid formula is a tautology, right?
Correct. Yeah. Tautology is another word for validity. Yeah. Okay, so the notion of satisfiability and validity, it uses the semantics of the logic. Okay, and an important point about these two definitions is that maybe you've already seen this, is that these are dual notions. Okay, so what I mean is, suppose you take a propositional logic formula alpha, then you can make this following assertion: alpha is valid if and only if negation of that formula alpha is not satisfiable. Okay, so these are essentially dual notions. So this has a very simple proof. So suppose alpha is not valid, then by definition, what does it mean? It means that there is some valuation where alpha does not hold, right? Okay, but then that implies that, so I should not write it this way, but so that implies that V satisfies not alpha. Okay, because alpha does not hold, that implies that V satisfies not alpha, and that means that not alpha is satisfiable. Okay, so, and I mean, I just explained one direction of the proof, but the same argument, you can simply reverse it, right? So the notion of validity and satisfiability is, these are dual notions, which is very important when you're looking at algorithmic questions. So for instance, if you're looking at a procedure to check for satisfiability, well, the same procedure can be used for checking validity and vice versa, right? So if you have a procedure to check for validity, the same procedure can be used for satisfiability, basically. Okay, so can you give me some examples of formulas which are, okay, simple example of a formula which is not satisfiable? Can someone give me a simple formula which is not satisfiable?
P and not P.
Correct. So P and not P is a formula which is not satisfiable, simply because, well, if you assign true to P, then the formula is false. If you assign false to P, then one. So it's a conjunction, right? So that is not satisfiable. So if you just look at a proposition P, that's always satisfiable, right? P and not P is not satisfiable because you have a conjunction, and the interpretation of the conjunction is that both have to hold, right? And P or not P is valid. So you take any valuation, this is going to be satisfied. Okay. So here are these are some simple examples. Okay. There is this important notion of semantic equivalence, which is very simple. We say that two formulas, alpha and beta, are semantically equivalent if for all valuations, the valuation satisfies alpha if and only if the valuation satisfies beta. So basically, alpha and beta are the same. The meaning of alpha and beta are the same. It might be syntactically different. That's what we're saying. Okay. That's the notion of semantic equivalence. So using this notion of semantic equivalence, you can define various other operators which are very convenient. So for instance, the way I defined it, things like implication were not there, right, in the syntax. So if you just go with my definition, you can't write implication in your formulas, and usually it's very convenient to have logical implication. So these are called derived connectives. And one of the important derived connectives is implication, right? So alpha implies beta. You can define, so this is a definition, this is not equality. Okay. So you can define it as not alpha or beta. So what I'm saying is these two formulas, so this formula and this formula, these are semantically equivalent. So this is a definition. Okay. Alpha equivalent beta is simply well, you have alpha implies beta and beta implies alpha, right? And it turns out that this conjunction you don't really need, because you can derive it from negation and disjunction, which I'm sure everyone knows. So this can also be defined in terms of disjunction and negations. Okay, so an equivalent way of specifying, so there's a minimal syntax for propositional logic, would be simply to say that you have propositions, you have negation, and you have disjunction. So you have to put either disjunction or conjunction, doesn't matter which one. Okay, so this is another way of specifying the same thing that we've been looking at. Okay. So one more notion which is useful, not just in propositional logic, but even later, is the notion of logical consequence. We say that a formula alpha is a logical consequence of, in general, a set of formulas gamma. And the way you write it is gamma satisfies alpha. So this is how you write it. So gamma here is not a valuation, but a set of formulas. Okay. So this is a definition. So you write something like this: if for all valuations which satisfy, sorry, this should be, so for all valuations which satisfy gamma, it is also the case that the valuation satisfies alpha. Okay, and what do I mean by a valuation satisfies gamma? Because gamma is a set, I mean that it satisfies all formulas in the set. Okay. So alpha is a logical consequence of a set of formulas if, well, you look at any valuation which satisfies all the formulas in the set, it also satisfies the formula alpha. Fine, that's a notion of logical consequence. Okay, so let me give you a couple of examples, and then we can hopefully it will be clear. Let's look at this formula. So now I'm using implication, and so implication quite generously, because it makes it easier to understand what the formula is, right? So let's look at this formula, and my question is it satisfiable? Is this formula satisfiable? So I hope the semantics or the interpretation of implication is clear. If you have any questions, please ask. Is this formula satisfiable? Okay, so let's look at this valuation where I set P as true and Q as also, so both P and Q are true. then I claim that this valuation satisfies the formula. Why is that? Well, when both P and Q are true, this sub-formula P implies not Q is false, right? The valuation does not satisfy P implies not Q, right? Now, because it's an implication, if this sub-formula is not satisfied, it doesn't matter what the status is with this sub-formula, the entire implication is satisfied, right? So that's the interpretation of implication. So here is a valuation where the formula alpha is satisfied. Okay. Of course, this is not the only valuation. So if I take P to be false and Q to be true, then that satisfies this sub-formula P implies not Q, and it also satisfies this sub-formula Q or not P, because it's a disjunction there, right? So, and that means that the entire formula is satisfied. Okay, so this formula is satisfiable, and here are a couple of valuations where you can satisfy, using which you can satisfy the formula. Again, I hope it's clear. So what about the validity? Is alpha a valid formula? So any ideas? Is alpha a valid formula? Well,
yes,
if
it
you,
is.
yeah. Okay, so okay, so let's look at this particular valuation. Maybe I'm making a mistake, so you can tell me if I'm making a mistake. So when you said that satisfies this subformula P implies not Q, okay, but it does not satisfy this subformula Q or not P, and that means that this implication is not satisfied, right? So because you have true implies false, and that means the implication is false, basically. Right? So here is a valuation under which the formula is not satisfiable. Well, this particular valuation does not satisfy this formula, and therefore the formula is not valid. Okay. Okay, so let's look at another formula which is slightly more complicated. So again, these are just small formulas, right? So you can write very complicated expressions using this syntax, right? So here is a formula which says P implies Q implies R, or P implies Q. And my question is whether this formula is valid. Okay? Now you already see the difficulty, right? So how do you actually test whether a formula is satisfiable or valid? So we'll come to this in a minute because that's a very important question. But let me give you a kind of a different argument for this particular formula, which you can utilize simply because this has a nice structure. Okay. So it turns out that this formula is valid. So let me give you an argument why it is valid. So what does it mean to ask whether the formula is valid? What you are asking is whether it is the case that for all valuations, the valuation satisfies the formula alpha. Okay? So that's a question that you're asking. All right. And of course, if it's valid, it's also satisfiable, right? Because it is satisfied by all valuations. Okay. So I'm going to give an argument by assuming by contradiction. So suppose alpha is not valid. Okay. So what I'm going to argue, or what I want to claim is that this formula is a valid formula. Now, suppose it is not valid. Yeah. What does it mean? It means that there is some valuation under which, so there's some valuation V such that V does not satisfy alpha. That's what it means. Now, alpha has a very nice structure. if V does not satisfy this formula is a disjunction, right? It's a disjunction of two subformulas, right? So if V does not satisfy that formula, well, it means that V does not satisfy both the components, right? Both P implies Q implies R and P implies Q, right? That's from the semantics of disjunction, right? Okay, so if V, so let's look at this part first. If V does not satisfy P implies Q, then there's only one way that V cannot satisfy P implies Q. It has to be that V satisfies P and V does not satisfy Q. That's from the semantics of implication, right? So this defines a valuation, right? A partial valuation. So this insists that the valuation of P is true and the valuation of Q is false. Okay. Now let's look at this component, which is the first subformula. We are saying that V does not satisfy this subformula, and again, it's an implication. So the only way that this cannot be satisfied is if V satisfies P and V does not satisfy Q implies R. Yeah. Again, this is an implication. So the only way that V cannot satisfy Q implies R is if V satisfies Q and V does not satisfy R. Yeah. But from here, you see that, well, for this to happen, the valuation of Q has to be true, right? And for this to happen, the valuation of Q has to be false, which is a contradiction because you cannot have both true and false. Okay. So this contradicts our assumption that alpha is not valid and therefore alpha is valid. Yeah, so this is, I did not really, I did not enumerate all valuations to argue that this formula is valid, right? I gave you a different kind of an argument, okay? So this, of course, may not always work, but here is a nice proof, very simple and compact proof that which does not involve enumeration of valuation to show that this formula is valid. Okay, so any questions at this point?
What exactly
So I'll
is...
give you one more example of encoding a slightly more complicated problem into propositional logic, but any questions?
Yeah, hi. So what exactly is peculiar about this problem that made it easy to go about this kind of proof?
Okay, so let's look at another problem. So it turns out that propositional logic, even though it looks very simple, it is quite important in the sense that there are many problems which you can kind of encode as instances of propositional logic formulas. In particular, the satisfiability problem. Okay. So let me give you one such example, and this is the graph coloring problem. So this is like a standard problem in graph theory, right? So there are various graph theoretic problems which you can encode as problems in propositional logic. So what you're given is a graph so you have a set of vertices and a set of edges, right? What are these edges? These are so the set E is a binary relation basically, right? So it's a subset of W cross W. Yeah, so it's an edge set. And what we are going to look at is the question of three colorability of a graph. So you have three colors, let's say red, green, and blue. And we say that a graph is three colorable if there is some function going from the set of vertices to this set of colors, right? Red, green, and blue. Such that it satisfies the following constraint. And the constraint is for every edge. So an edge is a pair of vertices. So if there are two vertices which are connected by an edge, then they have different colors. Okay, so that's the only constraint. So you have this graph. What you want to do is color the vertices of the graph using three colors, and also satisfy the constraint that if two vertices are connected using an edge, then these two vertices get a different color. Okay. Okay, so what I'm going to show is that so what is the problem? I mean, the question that you're asking is, given a graph, does it have a is it 3 colorable, right? Or can you come up with this function which satisfies this constraint, right? And what I will show you is that this problem can be encoded as the satisfiability problem in propositional logic. Okay, so formally, given a graph, we can construct a formula alpha such that the graph is 3 colorable if and only if the formula is satisfiable. Okay. And this encoding is relatively simple, and I mean, if you think about it, you should be also able to do it in no time. What is the basic idea behind this encoding? Well, you have the structure, this graph, right? So you have to associate certain propositions which capture the notion of coloring the graph, and you also have to associate certain propositions and formulas which kind of encode this constraint of colorability.
Hello.
So how do we do that? Well, for each vertex, what we can do is, for each vertex, we can associate 3 propositions. This basically encodes the fact that the vertices can be colored with either red, blue, or green. Again, there's a typo here. These should be RW, BW, GW, or I should just simply change it as V. So yeah, I'm sorry about this notation a bit. So for some reason I'm using V, and I'm also using V for valuation. But for this slide, V is just a vertex of this graph. Okay, so I'll share these slides, but I'll fix these things before I share the slides. Okay, so for every vertex, you associate 3 propositions, which is red, blue, and green. And you have a set of formulas. So basically, you want to encode the fact that every vertex get a color. It has to be exactly one color, right? So here is a formula which says that every vertex gets at least one color. So it is RV, or so this is a disjunction of these propositions. So this will ensure that every vertex gets at least one color. And you can write a bunch of formulas which ensures that every vertex get at most one color, right? For instance, you can say something like RV implies not GB, and RV implies not BV, right? So if your vertex is colored with red, then you cannot color it with green. And if your vertex is colored with red, then you cannot color it with blue, right? So you
Normally the proportional logic for the.
So for every vertex, you have this. You have 3 propositions and this bunch of formulas. Okay, so that basically kind of captures the fact that every vertex gets exactly one color. Now you have this constraint on edges, right? So again, you can write a bunch of formulas to capture that. So for instance, you can say that for every edge, which is this pair of the forms. So a pair of the form UW, you have a set of formulas, which is, well, if U is colored red, then W cannot be colored red. Yeah. Or if U is colored green, then W cannot be colored green. If U is colored blue, then W cannot be colored blue. Right. So this is the constraint, right? If 2 vertices are connected by an edge, then they cannot be of the same color. Okay. Okay. So you have all these formulas, and this is sorry. So for each vertex, you have a bunch of formulas. For each edge, you have a bunch of formulas. You simply take the conjunction of all these formulas, you get this big formula, so which I'm not really writing it down, but I hope that is. Am I audible?
Yes, sir, you are audible, but can you hear us?
Hello, Sunil.
Am I audible? Hey, Subhajit, I'm not audible, is it?
You are audible, but you are not able to hear us for some reason. So there were some questions, I think.
Oh, sorry. Okay, let me just check.
Yeah, there was a sound which has died now. I think that might help. Gaurav, somebody can you speak?
Yes, hello. Are you able to hear now?
Could you hear Gaurav now?
Hello? Hello? Um,
Gaurav, can you say it again?
yes. Actually, now I'm not able to hear. Oh, microphone is off right now.
Okay, you can hear Gaurav, right? Okay, cool. Thanks. Sure. Okay, sure. So I think some of you had some questions. Can you repeat? I mean, if you wanted to ask it again. Yeah, it's okay. Sound good to me.
Sunil sir, are you saying something?
Yeah, now I think we can't hear him.
Yes.
Yeah, I think so. That's
It's not showing that he's connected actually right now.
Oh, really? Maybe he dropped.
He's muted, it seems.
I'm not able to see name also. It's just showing the screen is shared. But,
Oh, sorry. Yeah, can you hear me now?
Yes.
Yeah, we can hear you.
Can you hear me now?
Yes.
Yes, we can hear you.
Okay, perfect. Yeah. Yeah. So, are there questions? Sorry for this confusion. Yeah. Are there questions?
Yes, sir. I had a question. Why
Yes.
do we need to take these three particular conditions that every vertex get at most one color?
No. So this. Okay. So what is the specification of the coloring problem? It is what you want is, or what you want to check is, if there is a function which maps every vertex to a value, right? In this set consisting of three values.
Yes, sir.
Yeah, so it's a function, right? So it can, so that means that every vertex is associated with exactly one color because it's a function, right?
Yes, sir. Yes, sir.
Yeah. So therefore, you have to somehow encode that, because I mean, propositions, you can have multiple propositions holding in a vertex, right? I mean.
Okay. I got it, sir. Got
Yeah.
it. Sir. Yes.
Yeah. So I mean, evaluation is basically you can think of it as a unary relation or whatever, a monadic relation. It's not a function, because you're mapping it to. I mean, another way of thinking of evaluation is to think of a subset of propositions, right? These are all the propositions which are true. So it's a subset in general, right? It's not one proposition.
Yes, sir. Understood.
Okay. Any other questions?
Yeah, hi. I had a question before in the slide before this, the proof that you made.
Okay.
I was wondering if there was something that is peculiar about this structure or whatever it is that made it possible for us to give the proof, or is it, or can you even is there anything that you can just verify to see if there's going to be a proof or not? I can see this being helpful later on.
Yeah, so let me just come back to that. That's what I want to do in the next slide. So let me just come back to that question, in a minute, and I'll try to answer the question. Yeah. Any other questions? Okay, so I hope this encoding is reasonably clear. I mean, what you get is a big formula, but it doesn't. I mean, the idea is pretty simple, right? So I hope that is clear. Okay, so finally, what you have is this theorem, which you can easily show that so G is three colorable if and only if this big formula alpha that you've constructed, which is the conjunction of all these formulas, right? So what I have described is what happens for a vertex and for each edge, And you have to take the conjunction of all these formulas for all vertices for all edges. That's this big formula alpha, and if and only if alpha is satisfiable. Okay, I mean, once you construct this formula, it's quite easy to show this, right? Okay, so the message behind this is so this three colorability is a standard question, right? In graph theory, you can give a graph theoretic answer to that question. Well, it's a decision question, right? Or what we have done is basically reduce it to satisfiability. Now, if you have a procedure to actually check whether a formula is satisfiable, you can simply use that to do this encoding, or to answer this three colorability question using this encoding. So that's what I meant. Okay. Any questions? Okay. So so these two questions. These are fundamental computational questions in propositional logic, which is that given a formula alpha, whether alpha is satisfiable, and given a formula alpha, whether alpha is valid. Yeah. So if you have efficient decision procedure, for instance, to check for satisfiability, there are many problems which you can encode as instances of satisfiability, and you can simply apply that decision procedure, right? So that's the attraction of having an efficient procedure for, let's say, satisfiability, right? And I already said, we already saw that satisfiability and validity, these are like dual notions. So if you have a procedure to solve satisfiability, you can basically use the same procedure to also show solve validity, right? In the general class of formulas, in propositional logic formulas. Okay. Okay. So what about this question, right? Well, it turns out that it's a hard question. Yeah. What would be a naive procedure to solve this problem? So an algorithm to check whether a formula is satisfiable. What would be the most naive algorithm or procedure to check this?
Enumerate all possible assignments.
Yeah, simply enumerate all possible valuations and check, right? So given a valuation, checking whether a formula is satisfiable in that valuation is easy, right? It's a polynomial time procedure. You simply have to evaluate, so that's fine. You simply what you do is enumerate all valuations and check whether it is satisfied. Here I have to be, to be precise, I have to be a bit careful, because the way I defined it, it's valuation is a function over set of all propositions, right? Which is an infinite set. Okay, so that means the set of valuations is going to be infinite, but it's obvious to see that you don't really need to define it that way. You can simply look at all the propositions occurring in the formula and define the function appropriately. Okay, so this is fine. Okay, so this check of checking whether a valuation satisfies a formula is a polynomial time check. So that's easy. And therefore, if you simply enumerate all valuations, well, you have a procedure. Now, how many valuations are there? If the length of, or the size of the formula is n, then basically you have 2 to the n valuations, right? Or order of 2 to the n valuations. So clearly, this is not an efficient algorithm. So this is basically a brute force search. It solves the problem. And it's highly inefficient, right? So the basic question is there an efficient procedure to solve satisfiability? And it turns out that the answer is no. And this is a famous theorem which was shown by Cook. It says that propositional satisfiability is NP complete. So again, I'm not going to get into the details of these complexity classes, but basically it says, so it's not an unconditional result. It's not saying that, no, it's not possible, right? That's not what it's saying. It's a conditional result. There is this class of NP-complete problems. And what it's saying is, so what the statement is essentially saying is, solving SAT is as hard as solving any other problem in this class, right? So a big open question in computer science is whether you can have efficient algorithms to solve problems which are NP-complete, so that we don't know. So that's this question of whether P equals NP, so that we don't know. But this statement is saying that it is unlikely that so SAT cannot have a easy solution unless every other problem in NP also which is NP complete also has an easy solution, right? Easy procedure to solve. So that's what it says. So basically, what this is saying is that well, as far as currently what we know is the best procedure is actually brute force search, right? I mean, you cannot do better than brute force search. So that's what this statement here is saying. Okay, so this is a hard problem. It's the logic looks very simple, and there are various problems which you can encode as satisfiability instances of satisfiability problem. But turns out that the actual SAT problem is hard. Okay, so that's where it is, right? So now if you go back to this example, now you see that, well, I mean, it's not possible to in general do this kind of reasoning, right? This formula has a very particular structure which involves implication and disjunction, and therefore it works, and it works only for this sort of when you have such structures, right? Otherwise, basically what you have to do is enumerate all valuations and check, and that's an expensive procedure. Okay, so any questions about this? So one thing that you should keep in mind about this statement is that it's the worst case complexity, right? So what it's saying is there are instances where you would basically take exponential time, right? So that's what it's saying. But of course, that doesn't mean that it is always exponential time. And in fact, there is this entire community. I mean, there's a lot of work in what is called on these tools called SAT solvers. And it turns out that these worst case instances don't really arise in practice so frequently. And therefore, SAT solvers actually work very fast. Okay, so theoretically, if you show that your problem can be kind of reduced to SAT, it's bad news because it says that you cannot have an efficient procedure, right? So that's the end of the chapter, because it's saying that there's no way you can have an efficient procedure, well, unless P equals NP. Yeah. But in practice, it's good news because SAT solvers are really fast, and so in most cases you won't end up, or you won't be encountering these bad instances or these hard instances of satisfiability. Okay. So I won't get into too much of details of SAT solvers, but that will be done today afternoon in the hands-on session. But I mean, I'll come back to SAT solving briefly after in some time. Any questions up to this point? Again, I hope.
Hello.
Yeah.
So I have a question, like, thinking about it, if we have a unsatisfiable formula, then I believe that it should lead to the pathological case, because like we would keep trying and we wouldn't get anything. But that is not what happens in like practice. So like, why is unsatisfiable, let's say, formulas also like usually speedy, like quick to be solved?
Okay, so can I again delay answering that question a bit? So let me just
Sure.
come back to that. Yeah.
Sure.
Okay. Yeah. Any other questions? Okay, so one thing that I want to quickly go through is so most of these SAT solvers, for instance, or pretty much any of these solvers require that you write your formulas in a particular way. Okay, so there are what are called these normal forms. So I want to briefly discuss these normal forms because there's something interesting going on with these normal forms with respect to these decision procedures, and that hopefully also gives you some kind of an answer to the question that you just asked about unsatisfiability, right? So the particular normal form that I will discuss in this lecture is what are called conjunctive normal forms. Again, probably you have seen this before. What are conjunctive normal forms? Well, it's a So you have the syntax for propositional logic. Now, what conjunctive normal form defines is a restriction on that syntax. Okay, so you can't simply write any formula, but the formula has to satisfy some additional constraints in the way you write the formula. Okay, and what are these constraints? CNF is defined, the basic building block of a CNF is what is called a literal, right? What is a literal? It can be either a proposition or its negation. Yeah, so it can be a proposition or a negation, that's a literal. Now, you combine literals to form what is called a clause. What is a clause? It's a disjunction of literals. Okay, so you have a disjunction of literals, that is what a clause, that is what is called a clause. So for example, P or Q is a clause because P is a literal, Q is a literal, it's a combination, it's a disjunction of literals. P or not Q or R is a clause because P, R, and not Q, these are literals, and you have combined these literals using disjunction. All right. Okay, and finally, what is a conjunctive normal form? You say that a formula is in conjunctive normal form if it is a conjunction of clauses. Fine. So your formula basically looks like this. You have your formula alpha is going to be a conjunction of what? Conjunction of clauses. So these are all clauses. And what is a clause? A clause is a disjunction of literals. Okay, so it's a conjunction of disjunction of literals. So that's how your formula looks like, right? So if your formula has this syntactic structure, then you would say that it is a conjunctive, it is in conjunctive normal form. Okay, so an example of a formula in conjunctive normal form, for instance, this one is a conjunctive normal form formula. Why is that? It's a combination of two clauses. So you have a clause here and you have a clause here, and these are clauses because these are just disjunctions of literals. Okay. Again, you can give a BNF sort of thing for CNF syntax, which is your literal can be either a proposition or its negation, and your clause can be either a literal or a disjunction of literal and a clause. And a conjunctive normal form formula is either a clause or a conjunction of a clause and a CNF formula. Okay, so this is a syntactic definition, right? I hope the definition itself is clear. I also hope that I'm audible. Now I'm concerned whether I'm audible.
Yes, you are.
Okay, thanks. Okay, so what is interesting about CNF is suppose I am guaranteed that I'm looking at formulas in CNF. Okay. Now I'm asking this question of validity, right? So this question: given alpha, is alpha valid? Where alpha is a CNF formula. All right. So alpha is not an arbitrary propositional logic formula, but I'm guaranteed that it's a CNF formula. It's a formula in CNF, and this is a question that I'm going to ask: whether alpha is valid, right? Okay. So now. You see that CNF by definition is a conjunction of clauses, right? And conjunction, the interpretation of conjunction is that it's an and, right? So the only way that a formula is valid is if all the conjuncts are valid. Okay, so that is obvious, right? So all the conjuncts have to be valid. So in order to check whether if a formula is valid, a formula in CNF is valid, what I have to do is to check that all the conjuncts are valid. Okay. How do I check if a conjunct is valid? Any ideas? Or sorry, how do I check that clause is valid? Sorry. So what I need to check is that all the clauses are valid formulas. How do I check if a clause is valid?
We'll check if any of the literals are valid, which involves the clause.
Say it again. Any of the literals are valid?
Yeah. Is it correct?
So literals cannot be valid, right? Because the literal is either a proposition or
it's right? Just has a valuation. Yeah.
So how do you check whether a clause is valid? Of course, you can enumerate all valuations and check.
Force,
yeah?
right?
Yeah, you can enumerate all valuations and check. That is brute force that we know. My question is more: is there any other way of doing it, or is there a better way of doing it?
Uh, don't we need a clause and its negation? Sorry, don't we need an atom and its negation in a clause to be sure of its validity?
So you can, so your answer is correct. So basically, you can exploit that fact that the clauses have a particular structure, right? Clause is not an arbitrary formula; it has a particular structure. What is the structure? It's a disjunction of literals, right? So it's a disjunction. So when do you say that a disjunction of literals? When can you say that a disjunction of literals is valid? Well, a disjunction of literals is valid only if, well, it's a characterization, even only if you have a proposition and its negation in that clause. Okay, so basically you have a structure of the form some P or not P, in which case it's going to be valid. Okay, so formally this is, so, okay, so here's the statement. So if you are given a formula in CNF, then checking if alpha is valid is can be done in polynomial time, right? So in general, we know that it's NP complete, but if it is in CNF, then it can be done in polynomial time. And the main observation is what we just mentioned, right? So you have, so you are looking at clauses and you have these literals, disjunction of literals. This is valid if and only if there are these indices ij such that the literal li is not of lj, right? So basically you have a p or not p sort of situation inside this clause. And that's the only way that is valid. Okay, so how do you check for validity in a CNF? Well, you simply linearly scan, right, this formula, and you can, it's a syntactic check. Yeah, you don't have to enumerate valuations. That's the whole point. It's a syntactic check, and it's an efficient check. Okay, fine. I hope everyone is convinced with that argument. Okay, so now the obvious question is, okay, so in general, so what about CNF? I mean, it's a syntactic restriction of propositional logic. Does it define a strict subclass of propositional logic, or what, right? Because you have this validity procedure which is very efficient for CNF. So does it define a strict subclass of propositional logic? It turns out that no, that's not the case. So every propositional logic formula can be converted into a formula in CNF, such that these two formulas are semantically equivalent, right? So of course, syntactically it'll look different, but semantically they are equivalent, right? So CNF defines. I mean, it's not a strict subclass. It's fine, right? So every formula can be converted into a CNF. Okay, so then what is the problem? So this doesn't seem to match up, right? You have NP completeness on one side, and then you have an efficient polynomial time check for CNF. So what is the problem? What goes wrong? Again, I mean, this translation to CNF is pretty straightforward. So let me not go into details. But for instance, the way you do it is take a formula and you kind of push all the negations in, right? So negations can only appear in front of propositions. So this you can do with what I call these De Morgan's law, and then you simply apply the distribution rules, which distributes disjunction over conjunction and so on. It's pretty straightforward. Okay. Again, I'll share these slides so you can go over it. So what is the catch? What is the problem? Anyone has any ideas?
CNF have a big size, like the equivalent CNF size is exponential.
Right. So that's the problem. When you translate a propositional logic formula into a CNF formula, you can, in principle, have an exponential blow up in the size of the formula. And that's where the exponent comes, right? So you can't just get away with it because, of course, it's known to be NP complete, right? So the translation can be exponential. Okay, but if you are given a CNF formula, then this validity is you can check efficiently. Similar to CNF, there is something called disjunctive normal form, and there again, for disjunctive normal form, satisfiability is easy to check, but validity is difficult. Okay, so just to give you a summary of these decision procedures. So if you take an arbitrary propositional logic formula you're looking at satisfiability and validity. These are the two questions. Both are NP complete. All right. If your formula is in CNF, then satisfiability is still NP complete, whereas validity is efficient polynomial time. If your formula is in disjunctive normal form, then satisfiability is efficient in polynomial time, validity is NP complete. So that's basically the picture, right? So I hope that kind of at least gives you a partial answer to the question that somebody was asking. I mean, so a formula not being satisfied is doesn't mean that you need an exponential search. It depends. For instance, it can depend on the structure, right? So satisfiability is polynomial time when you have a disjunctive normal form. Okay. Again, so it really depends on the structure of the formula, the particular formula. There are ways by which you can easily deduce that a formula is not satisfiable. So it does not necessarily mean that you need an exponential search immediately. Of course, there are instances where you need an exponential search. That's why it's the lower bound is NP hard. Okay, but that's not the case all the time. So there are cases when, I mean, this is just one instance, right? There are cases when you can do a syntactic check and check whether a formula is satisfiable. Okay, so I should also mention that already for 3CNF, the satisfiability problem is known to be NP complete. What is 3CNF? It's a conjunctive normal form where each clause has 3 literals. So you can't even have arbitrarily long clauses. So each clause has only 3 literals. Already for 3CNF, it's known to be NP complete. So this is inherently a hard problem. All right. Any questions? So SAT is like a canonical problem for that you see all the time. SAT happens to be the first problem which was shown to be NP complete, so that is Cook's theorem. And then using SAT, you can do all kinds of reductions to show that other problems are NP complete. But pretty much, I mean, if you look at complexity theory, I mean, SAT is like a fundamental problem. Okay. So propositional logic looks very simple. It has profound implications in all these fields: algorithms, complexity theory, verification, everywhere. And again, to mention that SAT solvers, right? So this is inherently hard, but that doesn't mean that it's difficult to solve in practice, simply because what we're talking about is worst case complexity, right? And in practice, it turns out that most of these instances don't arise. So you can actually solve using SAT solvers. You can actually solve SAT instances very fast. Okay. Any questions? So I'll come back to the SAT solvers in a minute to mention something else, but any questions at this point? Again, if someone can confirm that I'm audible, that'll be great.
Yes,
yeah, thanks. Yeah. Okay, so this is to do with the semantics. So what I want to mention briefly now is something to do with the syntax, and then we'll stop for the break. I think 10:30 there's a break. So I'll just quickly go over this syntax part. That's the other beauty of logic, right? So so you can do inferences, right? So this is something that you do every day in your daily life. What do I mean by inference and derivation? So consider the following two statements. Okay. If the train arrives late and there is no taxi, then John is late for his meeting. So this is the first statement. And the second statement is John is not late and the train arrived late, right? Okay, suppose somebody tells you these two statements. What is the immediate inference that you can make? Well, the inference is that, there was a taxi in the train station, let's say, right? So from these two statements, well, you can, without even thinking much, you can immediately make an inference, which is that, well, John got a taxi. That's why he arrived on time, even though the train was late. Okay. Now there's no, so these two statements, it doesn't have anything to do with the train. It doesn't have anything to do with John, whatever, right? You can abstract out from this specific instance of train, John, and so on. And if you do that, what you really get is an assertion in propositional logic, right? So, for instance, train arriving late, you can think of it as a proposition. It's either true or false. there is no taxi or there is a taxi, you can think of it as a proposition. It's either true or false. So let's say it's a not Q. There is no taxi is not Q, right? John is late for the meeting. Again, it's a proposition, right? It's either true or false. So let's say it's a proposition R. Okay. So for this first statement, it's essentially what it's saying is P and not Q implies R. That's what this is saying. So it can be anything, right? It can be train, it can be John, it can be taxi, it can be anything, right? So this is the abstraction that you've done. All that it, as far as inference or deduction is concerned, all that matters is the structure. It has a structure that P and not Q implies R. That's what the first statement says, right? What about the second statement? Well, it says John is not late and the train arrived late. So John is not late. Let's say again, it's a proposition. It's either true or false. Let's say it's, well, we already have this proposition R, so it is negation of that proposition. And the train arrived late. This again, we already have a proposition, right? P. Okay. So now forget about these two sentences and the English semantic of these two sentences. After this abstraction, what do we have? We have these two formulas, right? P and not Q implies R, not R and P. These two are the formulas that we have. These are two formulas that we have. And what we are saying is, well, with these two formulas, I can reduce that Q holds. Okay. Now, if you use your semantics, then it is pretty straightforward to reduce Q, right? But so the question that we want to ask is that can we formulate a procedure by which these deductions can be kind of automated, right? Or in other words, I don't want to use the semantics. Can I do these kind of reductions or deductions using just the syntax of the logic? Okay, so that's the basic idea behind inference, and you can do this, and these are called proof systems. So far, what we've been discussing about satisfiability, validity, all these have to do with the semantics, right? And now I want to shift from semantics into symbol manipulation. Okay, so what I'm asking is, can you do derivations using just symbol manipulations without applying the semantics? Okay, by just looking at the syntax and doing some symbol manipulations, can you make or can you derive assertions? Can you make assertions? So that's what that's the question. Okay, and that is what is done in a proof system. So what is a proof system? It consists of a couple of things. You can have a set of axioms. You can think of it as validities, tautologies, whatever. But I mean, at the moment, we don't have any semantics. Okay, we are not using semantics. So these are just formulas. Axioms are formulas. And you have what are called inference rules. Okay. Okay. So now we have a notion of derivation. So what is a derivation? So given a set of formulas as premises, so gamma is a set of formulas. I'm going to explain what it means to say that a formula alpha can be derived from this set of premises gamma. Okay, this is the notation that I'm going to be using. Gamma entails beta. Alpha should be. So this should be alpha. Okay, so what is a derivation? It's simply a finite sequence of formulas so it's a finite sequence of formulas beta 1, beta 2, beta n, and so on, where the last formula here is alpha. Okay, so that's your derivation of alpha. So the last formula has to be alpha. What about all these formulas, beta 1, 2, beta n minus 1? Well, it can be either an element of your premise, gamma. Gamma is a set of formulas. It can be either an element of gamma. It can be an instance of your axiom, or it is obtained by applying one of the inference rules. Okay, so you have this sequence of formulas that you have written. The last formula has to be the formula that you want to derive, which is alpha. And in between, well, you can use the formulas in your premises. You can use axioms, or you can use rules to derive new formulas. So that's basically what it says. Okay, I'll give you an example in a minute. But this is basically the idea of derivation. Okay, so the important point is you're not using the semantics. Okay. You can think of it as, for instance, a proof, right? A mathematical proof. I mean, in mathematics, don't think of logic, but for instance, in mathematics, how do you do proofs? Okay, so let me give you an example. Hopefully that clarifies what I'm talking about. What I want to define is, let's say, a rule which involves conjunction. Okay. Okay, so suppose I want to prove a property which involves the conjunction of two properties, right? So phi and c. So if suppose I want to prove the conjunction of phi and c. Yeah. Well, how do you prove in mathematics? How do you prove a conjunction of two properties? Well, if you already have a proof of phi and you already have a proof of c, then you can combine these two proofs to get a proof of phi and c, right? So that's basically what this rule is saying. Okay. So again, I'm not using the semantics of phi and c. Well, if I can already derive phi and if I can already derive c, then I can use this rule. Here is a rule to derive the conjunction of these two formulas. Okay, so this is a rule, right? Similarly, if I already have a proof of the conjunction, well, that means I have inside that proof, I have a proof of phi and a proof of c, right? So I can derive a proof of phi by simply eliminating this conjunction. This is another rule. Okay, this is an inference rule, right? And it's the same for the, so this is elimination of conjunction to get phi, and similarly you can eliminate conjunction to get c. All right, so here are three inference rules. Now let me give you an example of a derivation. Yeah. Okay, so what I want to derive is this statement here. I have two premises, P and Q and R, and S and T, right? From this, what I want to derive is this conjunction Q and S. All right. So I'm going to give you a proof of this statement here, right? So there are two premises. This is what I want to derive, Q and S, and what I can do is use these three rules. So I have three deduction rules: one for introducing conjunction and two for eliminating conjunction. Does this make sense? Okay, so let me give you a proof, and then you can ask me questions if something is not clear. So what did we say is a proof? Well, it's a sequence of formulas. Okay, so here I have 6 formulas. The last formula here is what I want to derive, Q and S. So this is Q and S. All right. And all these formulas up to 5, it can be either an instance of your premise, or it has to be obtained from applying these rules, one of these 3 rules. Okay, so that's the derivation. Fine. Okay, so let's list out the premise. We have 2 premises. Okay, these are our premises. Now, if I apply this rule, conjunction elimination, on this formula 1, then what I get is P and Q, right? Because conjunction elimination says, well, I can simply eliminate R. Yeah, so I get P and Q. Okay, now if I apply conjunction elimination 2 on this formula P and Q, then I can derive Q. I again apply conjunction elimination 1 on the formula S and T, I can derive S. Okay, so this is what I have. So I have a sequence of formulas that, how did I derive? I mean, I'm just using the rules to derive these formulas, and I have these 2 premises, right? Starting with these 2 premises, I've only used the rules to derive the sequence of formulas. Now, if I apply conjunction introduction to the formulas that I've already derived in 4 and 5, then what I get is Q and S, okay, and which is what I want. So here is a proof of this statement. So this is what I mean by a proof. So nowhere am I using the semantics of these formulas. It's just simple manipulation, right? And what am I doing? I'm simply applying rules which I've already defined. Okay, is this clear? Any questions about what it means to write a proof of this form?
I'm a bit confused about how did we go from step 4 to step 5? What rule did we use?
Step 4 to so it's not step 4 to step 5. It is about 5, right? I can use any of the formulas which I have already derived.
Okay.
Okay. Yeah. So the rule that I'm using is conjunction elimination 1, which is this, on the formula that I've derived in 2, which is this S and T.
Okay.
Okay, so these rules, you can think of it as templates. I mean, these are like variables. You can instantiate it with anything. Okay, So these are like placeholders. You can put in any formula here.
Okay.
Okay. So there are these three rules, and here I'm using this rule, conjunction introduction, conjunction elimination 1, on the formula which I already have earlier, which is SNT. Yeah, I hope that's fine.
Okay. Thanks a lot.
Okay. Yeah. Yeah. So the important point here is, well, I'm not using the semantics at all, right? I'm just doing symbol manipulation, and here is a proof of this is what I wanted to show, and here is a proof. Okay. Okay. So you can give. I mean, basically, you can build such a system. So let me just skip these things, and what you can show is that. So this is the notion of derivability of proofs, right? And this is the semantic notion. Okay, we say that if you can derive a formula, so we say that a system of these rules and axioms and so on is sound if you can derive a formula, then it's also valid. All right, and the system is complete, well, if every validity can also be derived in your system. Okay. A useful property to have is a sound and complete proof system, because it says that you can interchange between the notion of derivability, which is a syntactic notion, and the notion of satisfiability or validity, which is a semantic notion, without any problem, because if you can derive something, it is valid, and every validity you can derive. Okay, so this notion of derivation is something purely symbolic, syntactic. The notion of validity and satisfaction is a semantic notion, but these precisely correspond with each other. That's what soundness and completeness says. Right. So it turns out there are proof systems which are sound and complete for propositional logic. So which means that. Well, you can automatically, or you can try to derive formulas. You can try to derive all the validities in an automatic fashion by simply doing symbol manipulation. So that's basically what it says. Okay, so probably I'll stop here. And the reason why I wanted to discuss that is this has there's some interesting observation about these kind of proof systems and the satisfiability problem. So that's that I'll do next after the break, I guess. Yeah. So any questions at this point?
Isn't the soundness,
Yeah.
or aren't the soundness and completeness properties of how we define the system itself, rather than the proof system? Like,
what do you mean by system?
I'm sorry. So we defined propositional logic, right? So we defined syntax and then semantics, and then we went on to do all these things. And now we're talking about proof systems, which are, I don't know, systematic applications of whatever we have defined. So the soundness and completeness come from the definitions, right?
It's both the definition and the proof system that you can define, right? I mean, what is a proof? You can only apply deduction rules. Yeah. You can either write axioms, which are already validities, which you have put in, or you can apply deduction rules, right? So you need to have these. I mean, you need to be able to give these deduction rules, which enable you to derive all validities. So you may or may not be able to do that, right? Depending on what kind of logic you're working with. So if you are able to do that, then you would say that the system is complete.
So in case let's say that we have missed out on completeness for the system. So
okay.
To rectify that, wouldn't you go back to the definitions, or would you go back to the definitions, or would you go back to the proof system and redefine the proof system?
So that depends. So that depends, right? So if you can argue that this logic does not have a proof system which is sound and complete, then you would go back to the definition of the logic. I mean, you might want to go back to the definition of the logic, right? But proof system is not a unique thing, right? I mean, it could be that the proof system that you built is not sound and complete, right? But there might be some other proof system which is sound and complete.
Yeah, that's where my question comes in. So your proof system is built on like the syntax and the semantics. Okay, so we talked about conjunctions and symbol in the previous slides when you were talking about symbol manipulation, you were talking about conjunctions and disjunctions, right? So we have already defined the semantics for it, and if for some reason this proof system that we have built based on this particular definition of conjunction and disjunction is wrong, then it means that the definition of conjunction and disjunction is wrong, right?
Not necessarily. So it depends on the proof system that you build. So, I mean, you need to put in a bunch of rules. So, for instance, if you don't put in enough rules, then you may not be able to derive all validities, right?
Oh, right. Okay. So, right. So you're talking about the inference rules.
Well, inference rules or axioms. I mean, there are two ways of doing this. So I don't know. So there is something called natural deduction. Yeah. So that is a proof system which is sound and complete for propositional logic. Maybe you've heard of this. What it has, it does not have any axioms. It just has inference rules. Okay. And what are these inference rules? It has basically inference rules for all logical operators. So introduction and elimination rules. And there are a couple of additional things for bottom, for deriving bottom and so on. Okay. So it does not have any axioms. It just has a bunch of, it has quite a lot of inference rules, right? That is one way of, that is one system. That is one proof system. Okay, that's not the unique proof system, right? You can define other proof systems. So there is a different kind of system, which is typically called Hilbert style system, which has a lot of axioms and just one inference rule, which is modus ponens. So it has just one inference rule, but it has like 3 or 4 axioms. And you can show that with these 4 axioms and this one inference rule, you can derive all validities of the system. Right. And now if you drop a couple of those axioms, then it's not complete anymore, right? I mean, simply because you cannot derive.
Right. Understood. Thank you.
Yeah. And so probably I should also mention about the soundness, right? I mean, what soundness is saying is whatever you can derive is valid, right? That is usually the easy part to show, because you have to just make sure that all the rules, the inference rules that you are giving, it preserves validity. I mean, it's not that you can derive arbitrary things, right? The inference rules, as long as it preserves validity, then your system will be sound. So the difficulty is typically the completeness part, where you want to show that every validity can be symbolically kind of derived in your system.
Can I just ask you a vague question? I'm not really sure. Are Gödel's incompleteness theorem applied in these propositional systems?
No, I mean, that happens for first order logic, and the definition of completeness there is different. I mean, it's a different interpretation of completeness.
Okay, so I mean, what vaguely I know is that you can't always list out all the axioms and find all the true statements that are also derivable. You have to.
So that's not what Gödel's incompleteness theorem says. So I will come to first order logic in the next session.
Okay.
But I mean, there also in first order logic also you can show that there are proof systems which are sound and complete.
Okay.
So that's not what Gödel's incompleteness theorem says. That's more of the model theoretic meaning of completeness. So that's slightly different. So what it says is all formulas, I mean, you can either derive a formula or its negation, which is slightly different from talking about deriving validities.
Okay.
So that is what Gödel's incompleteness theorem says, that you cannot do that. I mean, there are systems where you cannot do that. The completeness is also due to Gödel. So there is also a Gödel's completeness theorem for first order logic, which is this interpretation that I just mentioned.
Okay. Thanks.
Any other questions?
So, hello, am I audible?
Yeah, yes.
Yeah, so sir, like in the previous slide, like whatever we entail from the inference rule, so it typically means that the distinctions of all the inference rules implies that the entailed the proportional logic, right? Or it's like, so is it, so am I like interpreting it correctly, or like?
Can you repeat? So which slide? This one?
Yeah, like the definitions of the where we started the syntax checking. So
the definition of derivation. Okay.
So here we said basically that whatever we are entailing from the inference rule. So I'm just basically trying to interpret. So is it like the conjunctions of this inference rules implies the entailed proportional logic?
Correct. So so you have premises which are like your assumptions. Yeah. So under these assumptions, I want to prove something. That's what it's saying, right? So you can use premises and you can use inference rules. Inference rules are basically saying that, well, if you have already derived something, then you can apply the inference rule on the derived formula. So that's what it's saying.
Okay, so how exactly it is syntax checking? So like,
because for instance, this one, right? So this, this is a inference rule. Yeah. What is this saying? If you already have derived C and C in earlier steps of your proof, then I can apply this rule in order to get this conjunction of this conjunction. So I'm not using the semantics of conjunction here. It's just a rule, right? I'm just applying this rule. Okay. Yeah. So how do I get, so in this example, for instance, how do I get this formula? Yeah, I get this formula by applying this rule on two formulas which I've already derived, and these two formulas are the formulas I derived in step 4 and 5. So Q is already derived, S is already derived. If that is the case, then I can simply apply this rule to get the conjunction. That's what I'm saying.
Okay, sir.
Okay, so I'm not saying that Q is true. I'm not saying that S is true, and therefore by semantics Q and S is true. That's not what I'm saying. Yeah.
Yes, sir.
I was able to derive Q somehow. Yeah. I was able to derive S somehow in this proof. Well, if you have already derived Q and S, then I can also derive Q and S by simply applying this rule. That's what I'm saying.
Thanks.
Okay. So this is the part which is symbol manipulation, right? I mean, I'm just applying rules. The part which connects the symbol manipulation to the semantics is this assertion of soundness and completeness. So if you have a proof system, if your proof system is sound and complete, then you can switch between semantics and derivability whichever way you want, because whatever you can derive is going to be valid, and every validity you can derive. So that's what soundness and completeness is.
Okay, sir. Thank you.
Yeah.
Hello.
Yeah.
Could you give an example of like gamma infers alpha, because I think I'm getting confused about what we mean by that notion.
Yeah. So for instance, this example, right? So this would be your gamma. Let me just write this down. So this would be your gamma. This is this consists of two formulas, right?
Yes.
So this would be your gamma. This is a set. I mean, set consisting of these two formulas.
Mm-hmm.
And your alpha would be this formula Q and S. This is your alpha.
No, what I meant was like I understood the derivation part, but I'm a bit confused about the other side, the infer side, the turnstile symbol.
Oh, okay, so this one is it? This one is it?
Yes.
This is the notion of logical consequence, which I defined, I think, in the beginning. So this just means that gamma is a set of formula. Okay.
Mm-hmm.
So this is the semantics, right? So this says that well, you look at all valuations which satisfy all the formulas in gamma, because gamma is a set of formulas. That valuation also satisfy alpha. That's what it means.
Okay.
So it's a notion. It's like a restricted validity, right? Yeah. So I mean, if gamma is, for instance, the empty set, then you get the notion of validity, right? Mm-hmm. So this is a more stronger statement. You can kind of so I mean, you can simply make the statement for when gamma is empty also, right? So then you have a standard notion, right? So if gamma is empty, then what you get is if you can derive alpha with no premise, then this implies that alpha is valid. Okay, but you can make a stronger statement in terms of what is called restricted validity or logical consequence. Yeah. So for all valuations where all the formulas in gamma is true, alpha is also true, then you can derive alpha from the premises given in gamma. So that's what this is.
Okay, and I have a question that do we ever like what I have seen is that I have seen this derivation like in use, like in type inferences, and also I've seen derivation sets being used, but I've never seen the other side, like what we were just discussing about the like gamma infers alpha. So do we ever work from that like semantically?
Well, I mean, satisfiability problem is semantics, right? So if you want to, for instance, if you want to solve SAT, why would you want to solve SAT? It's a semantic problem, right?
Right.
Yeah. So that's why I'll come back to this. So SAT, there are various, I mean, SAT solvers, there are various approaches to SAT solving. One is to kind of use semantics to do SAT solving. And that is the main idea behind this DPLL algorithm, right? Which is one of the standard algorithms for SAT solving. The other is actually to use this kind of syntactic manipulation. So that's something that I will discuss. Yeah. So that's what I wanted to do next. Yeah.
All right. Thank you.
Yeah. Any other questions?
Hello.
Yeah.
Yeah. So I have a question that are there like efficient proof systems for propositional logic?
What is your definition of
I mean,
efficiency?
as in, I can efficiently derive any given some given some propositions, I can efficiently derive the conclusion from them using the inference rules.
Yeah, in general, not right, because then you will also solve a validity problem, right?
Oh yeah, right. Okay.
So, I mean, yeah. So in general, you cannot have sound and complete systems which are also efficient in that sense. But what this says is that it's recursively enumerable. I mean, in the sense of if there is I mean, eventually you can enumerate all validities. So that's all it says. It does not say that you can do it efficiently.
And also in the very beginning, you mentioned that the set of propositions is countable. Could you maybe elaborate a bit more on that? Like, what if what if it's not countable? Would it lead to a different kind of logic? Or
yeah, so then we can't do many of the things. So because I mean, see, for instance, all this enumeration requires a countable building block, right? So those things you cannot do. I mean, there are various other logics. So propositional logic probably you wouldn't want to do. So if you want to reason about continuous time and stuff like that, right? There are propositional logic is probably not what you want to use. And there are various other logics to do that. I'll try to give you a flavor of such logics in the next session. Yeah, I mean, I won't be doing continuous time because I mean we simply don't have time to get into it. But you can think of these as domain specific kind of logics, right? Specific, it's more restricted, or it's built specifically to verify certain domains. So that sort of thing. Am I audible? I hope I'm audible. I am audible, right?
Yeah, Sunil.
Okay, yeah.
Yes, sir.
Any other questions?
Hello, good morning. Would it be possible to share the notes before the class? As in, since these slides or notes are already prepared, can we get it before the class so that we can immediately go back or refer to as and when required?
I'm fine with sharing these. I'm sure maybe you can put it up on the webpage, I guess. So yeah.
Yeah, but I think that doesn't go for everybody. Sorry about that, because lot of us create. At least I do it like the last moment. So my slides are not prepared even 5 minutes before the talk. So so I can try to ask the instructors. I mean, for whoever can do that, we can try to share, but it may not happen for everybody.
And also, I mean, slides, it might be difficult to interpret the slides unless someone explains, right? Because these are not lecture notes. So
Exactly.
it might actually make sense to look at the slides after the lecture. So I guess that most people would not have a problem with that. Yeah.